All right, guys. I apologize. I don't know what happened to the link. Maybe I sent it out to the wrong class. I posted two links and sent them out to two different places. So I don't know what happened, but I apologize. And this thing is being recorded, so if anyone misses it, they can catch it on YouTube. We were talking about magnetism. I want to review a couple of the main ideas that we talked about, and I want to proceed with our conversation. So if you have pen and paper, take notes. We did a couple things. First of all, we mentioned that the cause of any and every magnetic field is charge and motion. We started with that premise. I showed you a model of a bar magnet, and we looked at some vocabulary. So I drew a bar magnet. We mentioned that magnets have poles, north and south pole. So we talked about that. We looked at what we call lines of force that radiate from the magnet. They have direction. They leave the north pole and they come into the south pole. So I draw it with an arrow because there's actually direction to it. We call these lines of force. And so I drew a picture of something like this last time we were together. We talked about flux. And so we say that these lines or this field, these lines represent what we call magnetic flux. We use this symbol, phi, for flux. And we talked about two units of flux. We talked about the Weber, which is a unit for flux. We talked about the Maxwell, which is a unit for flux. The Weber is a MKS unit, and this is a CGS unit. That's not that important, but you'll see both of these for flux. So flux is important. The other thing that we talked about was the strength of what we call the magnetic field. We talked about, we called it flux per unit area. The flux per unit area is called the flux density. So if I take the flux divided by the area, I get flux density. And so we use the symbol B. And I mentioned to you that when we talk about a magnetic field or the strength of a magnetic field, what we're really talking about is flux density. And so the equation for flux density that you should write down, I think you may need this for your magnetism homework, will be the flux per unit area. And depending on what we use, whether we use Webers per meter squared or Maxwell's per centimeter squared, we noted that flux density will have units of Gauss, and this Gauss is a Maxwell centimeter squared, or you might have units of Teslas. And we said a Tesla is a Weber per meter squared. So this is just some of the vocabulary that we talked about. I also gave you a conversion factor that 1 times 10 to the 8th Maxwells is equivalent to 1 Weber. So these are all things you want to write down and make sure that you have access to these for the final exam. All right, so we talked about this, and what I want to do is I want to do just a few practice problems with these terms so we become familiar with it. But before we get into that, I want to go back to my original premise, because something should bother you a little bit. I mentioned to you that all magnetic fields are created by charge and motion. And basically, a charge and motion is electric current. We define current as charge and motion. So where's the current in this bar magnet? Where does the magnetic field originate? what's the cause of the magnetic field in a bar magnet when there's no wires hooked to it, there's no current flowing that I can see in it? Where does this magnetic field originate? And so I want to talk about that today, and then we'll do some practice with this stuff. So where does the magnetic field, if a magnetic field is caused by electric current, where is the electric current that causes the magnetic field around the bar magnet, a permanent magnet, is the question. And the answer to that is, if you look at the atoms that make up the bar magnet, and let's just look at any old atom, any atom. So any atom is going to have, the simplest atom, let's look at hydrogen. I have a nucleus, and I have an electron. And that electron is doing two things. The electron is spinning, and the electron is revolving. And so I draw, when we draw this atom, we usually draw the model like this. This represents the orbit of the electron. And so the electron is moving. It's not stationary. It's spinning and it's revolving. What's the difference between something spinning and revolving? What's the difference between those two terms? What is spinning? Anybody?
Rotating around its own axis.
The axis of rotation is through the object. It's rotating around its own axis, where if it's revolving, the axis of rotation is outside the object. So we say that the Earth spins about its own axis, but revolves around the sun. So the electron, if the electron were just revolving, let's say it had no spin. If the electron was just revolving around the nucleus, that constitutes an electric current. Think about it. The definition of current that I gave you the second week of class was current is charge in motion. Never ever did we say how the current had to move. We assumed that we were talking about translational motion. An object or a current moves from point A to point B, but any kind of motion constitutes electric current. So if I have an atom, and if the electron is revolving around the nucleus, then there's actually a tiny microscopic current that exists around the nucleus of an atom as the electron revolves around the nucleus. But not only is the electron revolving, let's say it wasn't revolving. Let's say it was just sitting there and it was spinning about its own axis. I know it's a strange way to think about it, but if I have an electron that's just sitting there with no motion, I have static charge. But if it's spinning, a spinning electron, believe it or not, constitutes electric current. By definition, electric current is charge in motion. Never did we say how the charge had to move. And so the fact that the electron is spinning, if it were not revolving, just spinning, it would create magnetic field around it because it's spinning. If it were just revolving and not spinning, it would create magnetic field around the atom because it's revolving. Both revolving and spinning constitute a current. Therefore, it creates a magnetic field. You can think of an atom, a single atom, as a microscopic little tiny bar magnet. And the superposition of the spinning motion and the revolving motion gives a net magnetic field or net magnetic effect to any and all atoms. All atoms have magnetic properties. And so it's customary in books, you can think of this atom as being just a tiny bar magnet like this with the north and the south pole. And it has magnetic field, just like the big bar magnet. Now, it's typical in books to draw this magnet, this little microscopic magnet or magnetic field that surrounds an atom. It's typical to draw them like schematically like this, a little diamond and then a little line like that. And this diamond represents the North Pole and this represents the South Pole. And when I draw this, I just draw an arrow because I'm lazy. I draw it like this, and that represents the north and south. So I'm saying any atom can be thought about as a little tiny bar magnet. And when you look at it like that, that's called a magnetic domain. A magnetic domain is the magnetic field that exists around any and all atoms because they have charge and the charge is moving. It's revolving and it's spinning. So every atom is a little tiny magnet, a little tiny microscopic magnet. Well, okay, so I have atoms in here in this bar magnet. Those atoms have electrons. Those electrons are spinning, those electrons are revolving, and that makes up the magnetic field. The sum total of all that makes up the magnetic field around any bar magnet. So there's an explanation for you. But you still shouldn't be satisfied with that explanation. It should still bother you because you can say that about anything. This marker has exactly the same properties as that magnet. The marker is composed of atoms. Those atoms have electrons. Those electrons are spinning and revolving. Why is it that there's a magnetic field that exists around the permanent magnet, but yet there is no magnetic field that exists around the marker? Why is it that I can take the permanent magnet and I can pick up a paper clip, I can pick up metal, but I cannot do the same thing with the marker? What's the difference between the marker and the actual permanent magnet when we consider magnetism? And the answer is the orientation of these magnetic dipoles. I want to do a little thought experiment with you. Consider this. Imagine I had two really skinny magnets. I'm going to draw the magnets. I'm going to shade in the North Pole. But I got a super thin bar magnet. So if I had a super thin bar magnet, really thin bar magnet, and let's say this is the North Pole. That's my North Pole, here's my South Pole. And so I can represent that as a magnetic dipole like that or like that. So I got a North Pole like that and the South Pole. And let's say I pick up a paper clip with that really thin magnet. So I got a paper clip stuck to the magnet. While that paper clip is stuck to the magnet, I take a second really thin bar magnet and I do this. I put it right up against the first one. They're going to stick together if on the second magnet I put its North Pole down here. Because you know that the North and South will attract. So if I take two really skinny magnets, North Pole, I turn it like this, and I put them together, they'll stick together. But what you will find is, if I do that with two really thin magnets, that paper clip's going to fall off. It'll fall off. Does anybody know, or do you think you know, why would that happen? Why would it fall off? What's happening here?
The north and south cancel out each other's magnetic polarity.
Exactly right. If you didn't hear it, I think that was Jake. I'm not. So I have basically, think of these magnetic dipoles. I have a North Pole and I have a South Pole. And those are, if you know what a vector is, these things are actually working against each other. So if I have a North Pole in one direction, north, south, and North Pole in the opposite direction, north, south, when I put those together, it's just like putting two charges, negative and positive together, they cancel out. So what's happening in here, in this bar magnet? Mother Nature has it set such that all these magnetic domains inside of this bar magnet are all pointing in the same direction like this. They're all pointing in the same direction. In the permanent magnet, they're in the same direction. So what I get is a net North Pole here and a net South Pole here. Whereas in the marker or anything that's not magnetic, what you have is a situation where, let's say you have a piece of metal. I may have one magnetic domain oriented like that, but somewhere else there's one in the opposite direction. I might have one like that, but somewhere else in here there's one like that. So there's no net north, no net south, they all cancel out. And so there's no net magnetic field here. Nature allows certain materials, though. These magnetic domains are locked in this orientation permanently, hence we call this a permanent magnet. But in some materials, especially metal, soft metal like iron, nature has it such that, let's say I have a piece of metal. Iron is a good example. So if I have a piece of soft iron and I try to pick up a paper clip, nothing happens because the magnetic domains are randomly oriented, and basically there's no net north or net south. They all cancel each other out. But what you can do is take another magnet like this. You can take a magnet and put it near the metal. Here's a iron. I can take a magnet, a north pole, and put it in close proximity to this piece of metal. And in some materials like iron, nature allows these magnetic domains to actually spin around, to orient themselves. And that's exactly what will happen. If you leave this metal near the magnet, over time what will happen is these south-seeking pole of the magnetic domain will orient themselves because they're attracted by the north. They'll orient themselves in this direction. And now when you take the magnet, the permanent magnet away, you take it away, now you have a net north and a net south pole on the metal. And now you can take the piece of metal and do what you did with the magnet. You can actually take the piece of metal and pick up a paper clip. And the paper clip will stick to it because you magnetized the metal. The difference is these magnetic domains are locked in that position and they stay there. We say a permanent magnet, they stay there forever, but nothing's forever. But they stay oriented this way for a very, very long time, whereas in the metal that you've magnetized, you can play with this. You've probably done this before. Took a piece of metal and magnetized it, and you can pick up the paper clip. Then you lay it down, you go somewhere else, you come back a little while later and try to pick the paper clip up, nothing. Because what happens is all molecules and atoms, they're actually vibrating because they have thermal energy. Nothing sits still. If we're above absolute zero, there's this vibration going around, and what happens is these magnetic domains actually literally shake themselves back into a random orientation, and at that point, the metal is no longer magnetized. And so they actually use this. There's a lot of applications. Well, they don't use it as much anymore, but I don't know, I might be dating myself. I know Steve knows what a cassette tape is. Jacob might know what a cassette tape is. I definitely know what a cassette tape is. So we didn't always have CDs and MP3 and all the stuff that you guys, we actually would put music and information on a piece of plastic covered chemically. Basically, it was rust. It was metal. So cassette tape has this plastic or vinyl material with the chemical equivalent of rust. And you can actually send a current and orient these magnetic domains in direct proportion to information and use these magnetic domains to store information. You can actually do that. They used to do that for computer memory, for music, cassette tapes, 8-track tapes. This idea was used a long, I won't say a long time ago, but not too many moons ago. This is the way we recorded information using these magnetic domains. So if you're wondering a little bit of the physics behind this, well, there you go. Now, what I want to do is, if you had a chance to print out the practice sheet, there's a practice sheet. I don't know if you had a chance to print it out, but there are 4 problems on this practice sheet on Blackboard under the link for magnetism. If you take that out, I want to look at problem number 1 and 2. So if you have that handy, take that out. If you don't have it handy, you can print it out real fast. Print it out, or you can open up your browser, or I'll just read it. I'll give you a second to get it in front of you, and I'll just read it. And we'll do a calculation or two, and then that's all I want to do with permanent magnetism. I want to move on to the next topic, which is called electromagnetism, because that's where this stuff gets really, really cool. So let's do some calculations with this, just for practice. And then we'll move on to electromagnetism.
So does a lodestone actually follow the same rules as iron, with it being already magnetic?
Hold on, I can't hear you. Let me turn I got my speakers all the way up, but let me turn my computer volume up. I hope I don't get any feedback. Now, will you repeat your question, please?
Yeah, a lodestone. It's a magnetic rock.
A load cell, yeah.
Does
Yeah.
it follow the same rules? Like, can you demagnetize it?
Now, I'm not sure about that. What they call lodestones, the Greeks would hang those from strings, and they were familiar with the magnetic fields from those lodestones. I'm sure if go ahead.
They used to use the lodestones as compasses because they were already magnetized and they could easily find north that way.
Yeah, yeah. So yeah, that's something you can research. I don't know if you can actually magnetize. I think the lodestones themselves are magnets. Since you bring that up, here's another interesting two other interesting points while you guys are looking for the paper. Since you brought up lodestones. First of all, I know most of you are familiar with the fact that the Earth is a giant magnet. What you might not know is that if I look at the Earth as a magnet, and I know the geographic North Pole is there, and the geographic South Pole is there, where do you think the magnetic North Pole is? Where's magnetic North? Well, a lot of people will say it's not to the axis. It's a few degrees to the left or to the right. And if you thought that, you'd actually be wrong, because the Earth, if I drew the Earth as a bar magnet, I would actually have to draw it like this, with the North Pole here and the
Magnetic
South
North
Pole
Pole
there.
is always moving.
I didn't hear what you said.
Magnetic north never stays in the same spot. It's constantly moving.
Okay, well, I don't know what you mean by moving. Well, I was showing that the magnetic north is actually at the geographic south. Now, as far as the poles moving, here's what I know. The North Pole and the South Pole, they actually do flip. Now, it doesn't flip it flips, I don't know what the cycle is, but it might be like every 100,000 years or something like that. These poles will actually flip. So 100,000 years from now, the North might be here and the South might be there. They flip. How do we know that though? How do we know they flip? How do we know that? How will we measure that? Well, that's a rhetorical question. Did someone say something?
Same direction, then they must switch.
Okay, I think your audio is a little bit muffled. I can't understand. I heard you say flip. And so, well, my point is, I don't want to get too far off track, because I can talk about this stuff all day. But you can actually take certain rocks, certain minerals were at one time liquid. They had iron, maybe iron was part of maybe a rock or lava, and the magnetic domains actually will orient themselves in the Earth's magnetic field. And then when that lava or rock cools down, becomes solid, those magnetic domains are actually locked at a certain magnitude and a certain angle. And geologists can actually take that and carbon date it and read the orientation of those magnetic domains and get an idea how the Earth's magnetic field was oriented at a certain time. So that's one interesting fact. Another interesting fact about magnetic fields is that you probably already know a lot of, some birds, it's believed, certain insects actually use the Earth's magnetic field. Like they have a sixth sense, a magnetic sense, and they use the Earth's magnetic field to navigate. And then one more interesting fact about magnetic field, and then just planets in general, not all planets have magnetic fields. Our magnetic field actually protects us from certain types of particles that I believe they come from the sun. Don't quote me on that, but there's certain exposures of the sun that send out these radioactive or these particles that can be harmful to us. But when they hit the Earth's magnetic field, Since there's a sideways force that acts on them and pretty much turns them around and shoots them back into outer space. So we can talk a whole lot about magnetic fields and interesting concepts and things about these magnetic fields. So hopefully you guys had enough time. I was kind of stalling there for you to get your paper out. If you don't, I'll read the first problem. The first problem on the magnetism practice sheet, it says you have a magnet, a permanent magnet, and they give you the flux. They say the magnet produces 40,000 Maxwells of magnetic flux, and they want you to convert this to Webers. So convert that to Webers for me. And these are just basic calculations. I mean, it's not pretty mind-boggling. I just want you to get used to the terminology and get used to using some of the math. So we got 40,000 Maxwells. 40,000 Maxwells. And we want to convert that to Weber units. So the question is, how many Webers is that? And you go ahead and do the math. I want to write this as 4 times 10 to the 1, 2, 3, 4 Maxwells. And if you remember, I gave you a conversion factor that said 1 times 10 to the 8th Maxwell is the same as 1 Weber. So that's what you want to use to do this. So go ahead and set up your conversion factor. I guess I'll do it like this. And I have on the bottom, I got 1 times 10 to the 8th Maxwells. And that's the same as a Weber. So what we're solving for is flux here, so I should probably put the symbol over here for flux. So you'll do that math, divide this by 1. I get 4 times, and when I bring that up, I get a negative 4. And then that would be Webers. So that's some basic calculation for you. Nothing earth-shaking about that. And then the other calculation they want you to do, this one there's flux density. So if you're looking at problem number 2, let's do that one. Did somebody text something? Oh, I thought somebody sent a message. The next problem, I'll read it in case you don't have the paper, and you can go ahead and calculate this for me. It says with a flux of 25 microweber through an area of 0.04 meters squared, they want you to calculate the flux density, and they want the unit in Teslas. So the flux is 25 microwebers. The area is 0.04 meters squared, and they want to find the flux density in Teslas. So go ahead and do that problem for me. You said the flux is 25 microwebers. And the area is 0.04 meters squared. And we're looking for the flux density. We're looking for B. When you talk about the magnetic field, the strength of the magnetic field, this is actually what you're talking about. You're not talking about that. You're talking about the number of flux lines per unit area. The more flux per unit area, the stronger the magnetic field. And so, of course, there's an equation for this that I gave you. It said that the flux density is the flux per unit area. I got 25 times 10 to the minus 6 Webers, and I'm going to divide that by 0.04, and this meter squared will be my unit. So if I take 25 times 10 to the minus 6 and divide that by 0.04 meters squared, help me out with the math, what would I get?
(6.25 times 10 to the negative 4).
All right, so notice my units are already in Weber meter squared, and we said that a Weber meter squared, that's a Tesla. So it's already in Tesla units. And that's the answer. So these are really trivial calculations. I mean, you got the equation, you got the number, you put it in, and your calculator doesn't work. What I'm really more interested in is that you guys get used to using the vocabulary, flux density, the units, Teslas, Gauss, that kind of stuff. So I won't give you a whole bunch of this stuff, but you do want to be familiar with that. All right. So there are some practice problems for you, and I'll give you a few more for the homework. Now, does anybody have any questions about permanent magnetism? Because I want to move on to the next topic, which is electromagnetism. Anybody have any comments or questions before I move on? So who can tell me what a vector is? Anybody heard of a vector? A vector. You might know what that is. I know some of you know because you had physics and calculus.
A vector represents more than one, like it can be direction and another property that you're looking at. So.
Okay, that's exactly right. So we have two types of
magnitude.
Say it again.
The other property is magnitude.
Okay, so the other property is magnitude. So a vector, the vector has basically, you need two pieces of information to represent it. You have magnitude or size, and you have direction. So some quantities in nature, you have to state two things to actually capture that quantity. So if I only need one thing, like magnitude, to represent a quantity, then we call that a scalar. Like, for instance, temperature is a scalar. It might be 65 degrees outside. You only need the 65 to represent the temperature. But if I was talking about velocity, velocity is actually a vector. To properly quote or state velocity, you need to say how fast something is going and in what direction. And so usually when we represent vectors, we use an arrow. And the arrow, the sense of the arrow, the direction, depends on how we draw the arrow. Like I can draw it like that. That might represent north. That might represent east, and so forth. So the direction I can represent by the sense of the vector, and the magnitude is represented by the length of it. So this is vector A. This is vector A right here. And the vector 2A would be in the same direction but be twice as long. Well, if anybody has worked with vectors before, you know that you can do math with vectors. And when you do math with vectors, you can add vectors together, you can subtract vectors, you can anything you can do with regular arithmetic, you can pretty much do with a vector. Now when it comes to multiplying vectors though, it's interesting. Because sometimes you multiply a vector times a vector, and you get another vector. Other times you multiply a vector times a vector, and you get something that's not a vector. We call that a scalar. It's not a vector. So if you guys had this in your math class or your physics class, when you do a vector times a vector, they call that the cross product. And when you do a vector times a vector and you get another vector, that's called the cross product. And usually the vector that you get, if I have a vector and a vector, I get another vector, and usually the vector is perpendicular to the plane of the other two vectors. Now, I don't want to get too complicated with this because you don't need to know this. If you know vectors and a little bit about, then this is probably like a review for you. But the point is this. Sometimes you multiply a vector times a vector and you get another vector. Sometimes you multiply a vector times a vector and you get something that's not a vector. For example, earlier in the semester, we talked about work. And what is work? Well, work is force times, now we said distance, but it's really force times displacement. And force is a vector, so when you draw a vector, you put an arrow over the top. And displacement, you put an arrow over the top. But if you take this vector times this vector, you get a number that's not a vector. It doesn't make sense to say you get 20 joules in a direction of 50. We don't say it like that. So here's a case where you multiply a vector times a vector, you get a scalar. Well, to make all that easy, because some people have had this stuff, some people haven't, to make all that easy so you don't have to know the math, they've actually made up some right-hand rule. And I want to talk about the right-hand rule. The right-hand rule is just a kind of a simplified way of being able to work with vectors without knowing any of this stuff that I'm trying to explain to you. So I want to talk about the right-hand rule. Before we get into that, let me show you what we're gonna dig into. Imagine that I have a conductor. Here's a wire. And I apply a voltage source to the wire. So what happens is current will flow through the wire. So here's current. Now I mentioned to you that every current flow causes a magnetic field. Associated with every current flow is a magnetic field. So there's actually a magnetic field that exists around that wire, and I want to talk about that magnetic field. But here's the cool thing. The magnetic field, B, the fluxity, is directly proportional to the current. In other words, if I increase the current, I increase the magnetic field. If I decrease the current, I decrease the magnetic field. And so all I got to do is this. If I have a variable source, I now have a magnetic field that I can control. Now that opens up a lot of stuff that we can talk about. But let me get back to that in a second. Let's go back to vectors. And I need a prop. Let me find a prop. Hold on a second. I usually have a student that I can get stuff from. And I'm in the basement by myself, so I don't have any props here.
Yeah, we're all out of physical books for you to play with.
Here's what I'm looking for right here. Usually somebody's in the front row, Steve or somebody's in the front row, and I can borrow their pen. So this is an arrow. Here's a vector, right? So I can have a current vector. I mean, actually I did it, didn't I? I have an arrow here. That's a current vector. I can have a current. It has magnitude and directions moving this way. So here's a vector, right? So if the vector is in the plane of the board, it's no problem. I can draw it in the plane of the board all day long. I can draw it like this. I can draw it any way I want in the plane of the board. But the problem is, what if I have a vector coming out of the board? What if I have a vector coming towards you like that, coming out of the plane of the board? The way I'm going to draw that is like this. If I have a vector coming towards you, what you would see, if this is the vector, and here's your eyeball, what you will see is that tip. And I'm going to draw that as a circle with a dot. That represents a vector coming towards you. If I take that vector and now it's going into the board, you're looking at the tail of the vector now. It's going away from you. I'm going to draw that like that. So I can draw a vector in the plane of the surface of the board. That's no problem. But if I want to represent a vector perpendicular to the board or coming out towards you, I'm going to draw that with a circle with a dot. If I want to represent a vector going into the board but perpendicular to the board, I'm going to draw that a circle with the X. And so now if you go back and you think about those little microscopic domains that I talked about, that magnetic domain, which the book will draw like that, I will draw like that. So there's my North Pole and there's my South Pole. Well, if this is your eyeball, if that's your eyeball and you're looking at that, what you're seeing is this. That magnetic flux line is coming towards your eye. Whereas if your eyeball is down here and you're looking at that South Pole, what you see is this. It's coming away from your eye. Here's magnetic flux flowing towards your eye. Here's magnetic flux flowing away from your eye. Now, let's talk about the right-hand rule. Now, understand that when I know as soon as I'm done, some of you are going to pick up a book or you're going to go to YouTube and you're going to look up right-hand rule. Well, you're going to be surprised. There's several right-hand rules, and there's actually left-hand rules. And let me explain the difference between the right-hand rule and the left-hand rule. In our class, we use conventional current flow. We assume incorrectly that current flows from positive to negative. If you assume conventional current flow, then you use the right-hand rule. If you assume electron flow, the actual direction of current flow is from negative to positive, then you use the left-hand rule. We will never, ever in this class use the left-hand rule. Everything for us is the right-hand rule. There's right-hand rules for conductors, a straight conductor. There's right-hand rules for coils. There's many right-hand rules, but basically all it is a simplified way of doing a vector multiplication that's a cross product. So I'm going to give you the one that we're going to use for a straight conductor. The right-hand rule for a straight conductor. Here's how it goes. You take your thumb and you put it in the direction of conventional current flow. It's a right-hand rule. If it's the other current flow, it's the left-hand rule. You take your thumb. You put it in the direction of conventional current flow, like you're hitchhiking. So current is flowing like that. Now your finger represents the direction of the flux. If I'm pointing towards you like that, you're looking at the tip of my finger, then you're looking at that North Pole coming towards you. If I'm pointing away from you like that, you're looking at the back of my hand, then you're looking at either the North Pole leaving you or you're looking at the South Pole right there. So what you do to find what the flux field looks like around this straight conductor, you take your right hand, your thumb goes in the direction of conventional current flow, and you wrap your finger around the conductor like that. And your thumb is always pointing in the direction of current flow. And if you see that, if you curl your fingers around, you'll see that my fingertips, which represent the tip of the arrow, is at the top of the conductor. And the back of my hand, which represents the bottom of the arrow, is at the bottom of the conductor. So when I draw the flux field around the conductor, I'm going to show the dots at the top and the X's at the bottom. So if you can imagine this, here's my conductor. If I use the right-hand rule on it, the flux is actually rotating around this way. So it's coming out of the top into the bottom. So if I do this, and I'll move it towards you, so you can see that flux is actually rotating around the conductor. This is my conductor. It's actually rotating around the conductor like that. What happens if I reverse the current? If I reverse the current, my dots move to the bottom and the X's move to the top. What happens if I increase the magnitude of the current? Well, I get a stronger magnetic field. So often what we do is this. instead of having a straight conductor, what if we do this? What if I take that conductor and I coil it? Let me erase this. If I coil this, imagine what happens. If I coil the wire, if I coil the wire like this, and let's put a battery here. And I have current flowing, and there's actually a right-hand rule for coils. You can look that up. There's a right-hand rule for coils, but here's my current flow. What you would see around this coil is this. And you're thinking to yourself, hey, that looks exactly like the flux field around the bar magnet. That's my point. You actually have a north pole here and a south pole here, and that flux field looks exactly like the flux field that we observed around that bar magnet. The difference is this. If I increase the current, I get a stronger flux density. If I decrease the current, I get a weaker flux density. If I flip the battery over and have the current coming into this way, instead of having a north-south polarity, I get a north here and a south there. So now I have magnetism that I can control. I can control the magnetic polarity. I can control the intensity of it. That, to me, is a whole new level of cool. There's a lot of devices and applications for this idea right here I'm showing you. I'll give you one right now. Imagine that you have a tube, like a paper towel tube, like the cardboard part of a paper towel. So you got a tube. I'll just draw it like this. And I'm going to wrap that tube with some copper wire. So I wrap it with wire. I'm just drawing a few coils, but you need a lot of wire to be coiled around there. And I'm going to add a switch and a power source to this. So I add a switch and a power source. So let's say I add that. Then what you can do is, hopefully this purple shows up. I can take a permanent magnet, and I'm going to take this permanent magnet and just put it in the middle of that tube like that. And let's say that, I don't know, this is north and south. And maybe I got a rod connected to this. So that's a metal rod.
It's going to bounce up and down in between.
Exactly. I don't know who that was, but depending on the direction of current, one direction will actually pull this thing down and leave it there, hold it there. And if I flip the battery over, it'll actually push it up. Now, that might not seem like a big deal to you, but that's huge right there. There's a trillion places where you see that. Perfect example, the power door locks in your car. How do the power door locks in your car work? Now, I'm not talking about, some foreign cars have vacuum locks. Those are old and outdated. But in most cars, they have electrically powered locks. This is exactly what you have. You move the switch one way, it pulls the lever down. When you move it the other way, either in the switch or through some other electronics, they reverse the polarity of the current, and then it pushes it up. So any kind of linear motor, this is a linear actuator is what this is. This is a type of motor that, not motor, what you can think of as a motor, that you can move in and you can move out, and you have total control over it. So this is big right here. It's really big. So I can go on and on and on and on with this electromagnetism.
You can also use those to completely wipe your computer.
Say again?
You can also use that setup that you just made to completely wipe your computer or any electrical device of all information.
And that's
the
true.
only reason
So,
I know it.
Well, some of you will know if you have a credit card, and on the back of the credit card is a magnetic strip. I don't know if you know that or not. And when they say, well, this one actually has a chip in it. To show you how small they can make things, you know how thin that is. There's actually a chip in the card. And a lot of people think, I don't know if you can see that in the camera, a lot of people think that that area is the actual chip, but the chip is just a little tiny square piece in the middle of that. The other part is just so the machine can connect to it. The chip is extremely small and it's extremely thin. But there's also information on the back of this card. So I don't know who that was that just mentioned that. But he's true. What he said is true. You can actually take a strong magnet and you can wipe across this. You can destroy all the information on here. The MRI machines, what's it called? Magnetic. What does that stand for? MRI, magnetic. I forget what it stands for. But when you use those MRI machines, they'll tell you can't have any credit cards, or even some of your thumb drives can be destroyed. The information can be destroyed by strong magnetic fields. So yeah, this is used a lot of different places. Now, I want to talk about something that is going to take me probably the rest of the time to go through it, but it's actually pretty important. I want to talk about two things. I don't know if I probably won't have time to get the second topic. I want to talk about rail guns. I told you I would. Some of you have been asked about rail guns, and I told you I would. I've actually built a rail gun. We'll talk a little bit about those. But what I want to talk about is something called motor action. So I'll probably ask about this on the final exam, and it's just you just gotta take good notes. So please, if you're some of you are signing off now, that's okay. Please go back and watch this on YouTube because I want to tell you a story. I got 20 minutes left. I'm going to go through this motor action because this actually will be our segue into AC. If you take me for AC, I'll talk about the opposite of motor action, which we'll talk about here shortly. If you're taking me for AC in the summer or in the fall, we're going to pick up with this exactly where I am now. We'll talk about it. So take good notes on this because it's probably not in your book. Now you got to understand the right hand rule to get this. So this is motor action.
I have a quick question before you go on to that. Is energy considered scalar or vector?
Energy is a scalar.
Ah, okay, I thought so. I was just double checking.
Yeah, energy is a scalar. That's a good question. Okay, now, so here's what I want to do. So I'll go slowly. I think we got enough time to go through this. And because on the exam, I'm gonna give you this problem, but I'll change something. And there's nowhere to read about this. You just kind of got to go by my notes on the board. So just if you follow my logic and my argument, this will make sense to you. Before I get into it, let's talk about a vector field. I don't know. Just imagine I had a bunch of, I don't even know what to use as an example. Let me think about it. Okay, suppose I have maybe the wind. I'm going to represent the wind as just a bunch of vectors. So there's the wind is blowing this way, and I got a plane, an airplane. Right? I got an airplane. Let's say this airplane by itself and no wind, if it had no wind, it's going to fly a lot faster than, let's just say it's flying at 100 miles per hour. So here's the vector, the velocity vector of the airplane, 100 miles per hour. And let's say the wind is blowing that way in the same direction at 50 miles per hour. What do you think is going to happen? What's going to happen?
The plane,
Go ahead, say it.
the plane's going to fly faster than 100 miles per hour.
Yeah,
Well,
relative to a person on the ground, when he's looking at the plane or she's looking at the plane, she's going to see the plane travel at 150 miles per hour. How is that so? Well, here's I have a vector field, and these vectors I call a strong field. When vectors are working together, they add up to give you a stronger effect. And so I have the 100 miles an hour that the plane is already going, and then in addition to that, I got another 50 miles an hour that the wind is going. that plane is going to move 150 miles per hour relative to somebody looking up at it on the ground. But if I did this, if I took the plane and now made the plane fly into the wind like this, and no wind at all, was flying this way at 100 miles an hour, if the wind started going the opposite direction at 50 miles per hour, a person on the ground will see this plane moving in that direction at 50 miles per hour. Now these vectors are working against each other. So it gives me a weak field. So when vectors are all working in the same direction, we get a strong field. They add up. When vectors are working against each other, we get a weak or weakened field. They subtract from each other. So if that example was clear to you, then follow this. Go back to the situation I had before when I had a conductor. I got this conductor. I got it hooked to a voltage source. Current is going to flow through the conductor. And it's going to create a magnetic field around the conductor. And if I ask you for the direction of the magnetic field, it's easy. All you got to do is the right-hand rule, and you can give it to me. But I want to change the geometry of the conductor. I want to bend this into a loop. I don't want a straight conductor. I want a loop conductor. So I'm going to change the geometry of the conductor like this. I'm going to bend it like this. So I'm going to bend that conductor like that, and then I'm going to put the battery back on it. So here's my battery. And now what's going to happen is the same thing that happened before. Current is going to leave the battery. On the top conductor is moving this way. Right here is going to move down. And on the bottom conductor is going to move this way, on this way back to the battery. Now just so I can reference these conductors, I'm going to call the top conductor, this one, I'm going to call that conductor A, and the bottom part of this, I'm going to call that B. All right? If you look at the current in conductor A, if you look at the current in conductor A, this is your eyeball, and you can see the current, what would you see? Wouldn't you see this? Wouldn't you see an arrow coming towards your eyeball? You would see that. And if you were looking at conductor B, looking at the current, what would you see? What would you see?
The one with the X instead of the dot.
You see the current leaving your eyeball, you see that. So in this orientation, to your eyeball, conductor A looks like this, conductor B looks like this, and this time instead of representing magnetic field, that dot represents current coming towards you in conductor A, and this X represents current leaving your eyeball in conductor B. So what I want to do now is take two permanent magnets. I got a magnet right here, and I got a magnet right here. This is a north pole, and that's a south pole. So between those two magnets, I'm going to have flux. Flux goes from north to south. Now what I'm going to do, I don't know how to show you this. So here's my coil, right? Here's my conductor A. Here's my conductor B. Here's my coil. Now this piece right here, even though we know we got that piece there because the current has to go through A, come down that part to get to B to get back to the battery. But I'm not interested in that part. So you ever seen a drawing where they have a cutaway or something? It's really there, but they show dotted lines, but it's a cutaway. That's what I'm going to do here. I'm going to take this, I'm going to turn it towards you like that. I'm going to rotate that coil, and I'm going to do a cutaway of that. I'm going to take it out. It's still there, but I don't want you to focus on that. I want you to focus on these two conductors. So what I'm going to do is take this coil. I'm going to move it so you're looking at the edge of it right here. You're looking at the edge of it. So I'm going to turn it towards the camera now. You're looking at it, and I'm going to flip it this way and put that over in the magnetic field. But I don't want you to focus on this piece, so I'm going to just get rid of that. It's still there, but I don't want you to focus on it. So what you'll see here is conductor A, if I do that, then I'll have one conductor here. I'll have one conductor here, and then this piece right here is like right there. And if this right here is conductor A, and this right here is conductor B, you told me that in conductor A, you see the current coming towards you. So over here in conductor A, what you would see is this. So current is going to come out of A, going to go through this piece, which is right there, and then go back into B. So you told me in conductor B, you see the current going away from you. So what you would see is this. So if you're drawing this on your paper, use the right-hand rule and give me the direction of the flux field around conductor A, and give me the direction of the flux field around conductor B. I'll be quiet for a minute while you, on your notes, I want you to draw the direction of the flux field around A, draw the direction of the flux field around B, and I'll pause for a second and then we'll look at it together. So if you use the right-hand rule, your thumb goes in the direction of conventional current flow, and your fingers wrap in the direction that the flux is spinning. And so in conductor A, it's coming out of the board. The dot says it's coming out of the board. So on the top of conductor A, my arrows are like this. On the bottom of conductor A, my arrows are like that. So there's a counterclockwise rotation of the flux field around that conductor that we call conductor A. If I do the same thing to conductor B, I get the opposite effect. This time my fingers are curling that way. So on the top, I have flux rotating that way, and on the bottom, I have flux rotating this way. Now, if you follow that right-hand rule, if you follow that, then what you will observe is two things. Number one, if you look at conductor A, the green marker lines represent the permanent flux field from these magnets. The purple, if you can, I don't know if you can tell that that's purple, but I show you the rotational flux field around each conductor A and B. On the bottom of A, conductor A, the flux produced around conductor A is in the same direction as the green flux produced by the permanent magnet. That's equivalent to two vector fields adding up. So what I get over here is a strong field. That's a strong magnetic field. Those two vectors add up. Here on the top, I got the permanent magnet green flux going that way, and on the top of conductor A, the rotating flux is going the opposite way. So they weaken each other. They subtract from each other. So here I get a weak field on conductor A. Let's look at conductor B. It's the opposite. On the top of conductor B, the green flux from the permanent magnet and the flux from conductor B are actually going in the same direction. So I have a strong field here. And at the bottom of conductor B, they're going in opposite directions. So I have a weak field here. Now, if you stand back and look at that, you'll notice something. In nature, the strong moves towards the weak. So I have a net force on conductor A from strong to weak like this. And I have a net force on conductor B, again from strong to weak, like this. But this is a rigid object. So what happens is I have a force this way, and I have a force that way. That thing is going to tend to want to rotate in that magnetic field. It'll actually spin around. Here's the cool thing. If I wanted to spin faster, guess what I do? Increase the current or voltage. If I wanted to spin slower, what do? Decrease the current or voltage. If I want this to spin in the other direction, what do? Change the polarity. I have total control of the rotation of this device. This is called motor action. Any basic DC motor, there's a little bit more to it than this, but any basic DC motor is based on this. This is a conceptual drawing. If you open up a motor, you'll see a little bit more than this. But the basic physics of it, there it is right there. With this, as I said before, this is a whole new level of cool. So remember this, I got about 4 minutes. What we're doing here now is we're putting in electrical energy, and this thing is going to spin. And this is the part, if we were actually face to face, I actually built a small motor. It's a model motor. And I would, if we were in the class, I would set this in front of you. When I talk about this, I would set this thing up, and I'll put the coil in the magnetic field, and the thing will just rotate until it flies off of the stand. You actually see this. You can go to YouTube and look up paperclip motor. If you're bored, since we're doing this, what they call a shelter in place, look up paperclip motor based on this. You see magnets, and you'll see the strong weak field that I'm talking about. But the last point I want to make is this. On this coil, I'm putting in electrical energy, and I'm getting out mechanical energy because this thing is turning. What I want to talk about, well, we'll end the magnetism discussion. We still got to talk about rail guns. We'll do that next video. But you can also do it the other way. If I put in electrical energy, this thing will spin. Well, guess what happens if over here I spin this? If I put in mechanical energy, I put in electrical energy, it spins, I get out mechanical energy. Well, if I spin this, if I put in mechanical energy, I actually get out electrical energy. This is called motor action. Electrical energy in, mechanical energy out. But when I put in mechanical energy out, electrical energy, that's called generator action. And that's where I said, if you take me for AC, that's what we'll pick up with. We actually get into this a little bit in the next video. I'm going to talk about a very important law, kind of what we'll start our AC topic with. So, on the exam, the final exam, there'll be a question on motor action. I'll talk about rail guns, but I'm not going to ask about that. I talk about that because people are interested in rail guns. I actually had one of my UC students build a rail gun after he heard me lecture about it. And I built one when I was in college, a small one. But this, I think, is important. This is basic stuff right here. So on the exam, there'll be a question on motor action. And so even though you're doing this at home, you have everything right there, you still got to understand the strong weak field thing, and you got to understand the right hand rule. There's a lot of ways I can answer this question on the motor action. But I can give you, you'll see, there's a lot of ways I can answer the question. So make sure you're crystal clear on the right hand rule and this idea of this dot arrow notation and all of that. If not, fortunately, we're YouTubing this. So you can go back and you can watch this over and over again. Whew, that's a lot. But I like this topic. This is one of my favorite DC topics. I think I'm done, guys. I have about 2 minutes. Does anybody have any questions or comments for me before we sign off?
I do have a question.
Okay. You say you do or you don't?
Yeah, I do have a question.
Go ahead.
Using the workbook, is it
You break it up.
turn in like disconnection? Am I still going to turn in like the labs and stuff, like using the like?
Is it really?
You have to change
Wait,
it.
Okay. I'm gonna. Wait a minute, hey, guys. If you have a question about the material, that's what I want. I don't want to record anything else on you. When I stop recording, we'll stop recording. You can ask me other questions. But anybody have any questions on the material? Okay, if nobody has any questions on the material, I'll stop recording, and then if you want to ask me something else, I don't want that all on YouTube. Let me stop recording.